Welcome to the deep dive. Today, we're digging into a technology that you hear a lot about in enterprise blockchain circles, Hyperledger Fabric.
Yeah, we've got a bunch of documentation, some guides, maybe even a bit of research paper detail here.
Right. And it's known for being a permissioned framework, quite different from things like Bitcoin or Ethereum.
Absolutely. Built very much with business consortia in mind. Understanding its core ideas is, I think, crucial to see where it fits.
So our mission today is really to unpack all this material, pull out the really important bits, and give you a clear sense of how Fabric actually works.
Yeah, get past the buzzwords and look under the hood. What are the components? How do they interact?
Exactly. We want those aha moments, understanding why certain design choices were made.
Okay, let's get into it. Where's the best place to start with Fabric's architecture? Seems pretty complex.
Well, the sources seem to agree. Start with the overall network concept. It's not one single thing.
Right. It's run by a collection of organizations, not a central authority. Think of it like a shared infrastructure for a group.
Okay, so multiple businesses working together, needing a shared trusted record of things.
Precisely. And the big idea is, instead of everyone having their own separate database and then trying to reconcile everything later, which is slow and risky, Fabric participants share a ledger.
A replicated ledger.
Exactly. Replicated copies. And not just the data, but also the programs, the business logic that updates that data. That's shared too.
That already sounds like it smooths things out compared to traditional ways businesses interact.
Definitely. The sources really emphasize that this reduces time, cost, and risk. You're building that shared truth right into the system's design.
Okay, let's zoom in on that shared ledger. The docs break it down, right? Two main parts.
That's right. First, you've got the world state. Think of this as a database, often CouchDB or maybe LevelDB, that holds the current value of all the assets or data being tracked.
So if we're tracking a car, the world state shows its current owner, its location right now.
Exactly. It's optimized for quick lookups of the latest information. Key value pairs, essentially.
Yeah.
But because it changes all the time,
You need the history.
you need the history. That's the second part. The blockchain. This is the immutable, ordered log of all the transactions that ever happened.
Tamper-evident, cryptographically linked blocks, the whole deal.
Yes, it records every change that led to the current world state. So you can always verify the history and reconstruct the state at any point. It's your audit trail.
So world state for what is true now, blockchain for how did we get here.
Perfect summary. One for speed, one for immutable proof.
Makes sense. Okay, who actually, holds these ledgers and runs the code?
That brings us to peers. Peers are the fundamental nodes in the network, and crucially, they're run by the participating organizations themselves.
So if my company joins, we deploy and manage our own peers.
Correct. Your peers connect your organization to the network. They host copies of the ledger, and they run the smart contracts, which Fabric calls Chaincode.
And each peer holds the ledger for the specific networks or channels it's part of.
Exactly right. A peer might be involved in several different channels, and it maintains a separate ledger instance for each one. They're the real workhorses from an organization's point of view.
Okay. Now, you mentioned ordering transactions. In many systems, that's tied up with validation. Fabric does it differently.
It does, and this is a really key design choice. Fabric has a separate component called the ordering service, made up of nodes called orderers.
Why separate them? What's the advantage for businesses?
Great question. In, say, proof-of-work systems, there's that whole race to propose a block, which can lead to uncertainty, maybe temporary forks. Fabric wants determinism for enterprise use.
Determinism, meaning a guaranteed single order?
Yes. The orderer's job is only to receive endorsed transactions from clients, agree on a definitive sequence for those transactions, bundle them into blocks, and then deliver those ordered blocks to the peers.
So the orderers don't actually execute the chain code or validate the transactions themselves?
Nope, they just order. This separation means that once a peer gets a block and validates the transactions inside it, which we'll get to, it knows that every other peer getting that same block will reach the exact same final state for the valid transactions.
No forks, ever.
Correct.
Yeah.
Ledger forks are prevented by this design. You get transaction finality much faster and more predictably. The docs point to Raft as the go-to consensus for the ordering service in production.
Raft. That's the leader-follower model, right?
Of course.
Tolerates node crashes.
Exactly. It elects a leader, followers replicate, it's crash fault tolerant, or CFT. As long as a quorum of orderer nodes are up, the service keeps running. Vital for reliability.
Okay, peers, ledgers, orderers, and you mentioned channels a couple of times. Let's unpack those.
Channels are all about privacy and compartmentalization. Think of them as private subnets within the broader Fabric network.
So my organization could be in one channel with, say, our direct suppliers and a completely different channel with our financial auditors.
Precisely. Each channel is a separate communication path with its own ledger, its own chain code, its own policies. Data shared on one channel is completely invisible to participants on another channel, even if they're part of the same overall Fabric deployment.
That sounds essential for business. You need that confidentiality.
Absolutely. It lets organizations share the underlying peer infrastructure, maybe even hosting, while keeping different business relationships or data types strictly segregated, efficient, and private.
Okay, privacy handled by channels. What about identity? How does Fabric know who is allowed to do what?
Right, this is the identity, trust, and governance layer. It starts with the membership service provider, or MSP.
MSP, what does that do?
In a permission system like Fabric, everyone interacting, peers, orderers, users, admins, needs a verifiable digital identity. The MSP is the component that defines an organization's identity structure. It maps digital identities, usually based on certificates, to specific roles within that organization.
So my company's MSP says this certificate belongs to one of our peers, or this one belongs to an administrator.
Exactly. It establishes who belongs to which organization and what capabilities they have, joining channels, deploying code, submitting transactions. Each org manages its own MSP.
And those digital identities come from CAs, certificate authorities.
Fundamentally, yes. CAs issue the actual digital certificates, typically X.509 standard certificates. These are used for signing transactions, authenticating nodes, everything identity related. And then there are also TLS certificates, again from CAs, just for securing the network communication itself.
But sources seem pretty emphatic. Use a real CA like Fabric CA in production, not the test tools.
Oh, absolutely critical. Tools like Cryptogen are just for quick prototypes. Production needs a proper, secure CA infrastructure. Often you'll even see a split and enrollment CA for the main identities and a separate TLS CA just for the secure transport layer. Better security hygiene.
Okay, identity sorted via MSPs and CAs. How do we enforce the rules based on these identities?
That's where policies come in. Policies are the rules engine of Fabric. They dictate who can do what under what conditions.
What are the main types of policies we need to know about?
The documentation highlights 3 key ones. First, endorsement policies. These are tied directly to chain code and are central to Fabric's transaction flow. An endorsement policy dictates which organization's peers must execute a transaction proposal and sign off on the result for it to be considered potentially valid.
So it's not enough for just any peer to run the code. It needs specific sign-offs.
Correct. For example, a policy might say need endorsement from org 1 80 towards 2. If a transaction only gets signed by org 1's peer, it will fail validation later, even if the execution itself was fine. It's a form of distributed consensus applied before ordering.
Got it. What about changing the network rules themselves, adding a new org, for instance?
That's controlled by modification policies. These define which identities, usually a group of administrators from the member orgs, must agree to make changes to the channel's configuration. Things like adding members, updating MSPs, changing other policies. It protects the network's own governance.
Governance over the governance rules. Makes sense. And the third type?
Signature policies. These are the building blocks used within other policies. They let you specify combinations of identities needed to satisfy a rule. You use syntax like org1msp.admin or org2msp.peer and combine them with logic like AND or node of M.
So you could say need signatures from 2 out of the 3 founding members admins.
Exactly. Allows for really flexible and granular control over who can authorize different actions.
Okay, identities policies. That sets the stage. Now, the actual business logic Fabric calls it chain code.
Right. Chain code is Fabric's term for smart contracts. It's the code that contains your business rules, the logic that interacts with the ledger, primarily reading from and writing to the world state.
So my transfer asset function or update shipment status logic lives in the chain code.
Precisely. And it runs on the peers. Client applications trigger specific functions within the deployed chain code to initiate transactions. Importantly, while the chain code itself is agreed upon, Fabric security relies just as much on the endorsement policies and validation checks, not solely on trusting the code itself.
How does new chain code get deployed or updated? It sounds like it needs agreement, too.
It does. There's a defined Chaincode Lifecycle. First, you package the code. Then, you install it on the peers that need to run it. But just installing isn't enough.
Okay.
The organizations on the channel then need to approve a definition for that chain code.
Yeah.
This definition specifies its name, version, sequence number, and, crucially, its endorsement policy.
So everyone has to agree on the rules before it goes live.
Yes. Once enough organizations approve the definition based on a specific lifecycle endorsement policy, often a majority, then one organization commits that definition to the channel. Only then is the chain code active. Updates mean proposing a new definition with an incremented sequence number and going through the approval cycle again.
That ensures shared control over the active business logic. Very enterprise-focused. But what if, even on one channel, some data is super sensitive? Like, 2 partners need to agree on a price, but the other 8 members shouldn't see it.
Exactly the problem private data collections, or PDCs, solve. This is a mechanism to allow a subset of organizations on a channel to share data privately amongst themselves.
So this private data, it doesn't go through the orderer. It doesn't end up on the main channel ledger for everyone to see.
Correct, on both counts. The actual private data is distributed peer-to-peer using a gossip protocol only among the authorized members of that specific collection. The orderer never sees it, and it's not stored in the main ledger state on peers outside the collection.
How does the rest of the channel know the transaction involving private data was valid if they can't see the data?
That's the clever bit. While the private data stays private, a cryptographic hash of that private data is included in the transaction on the main channel's blockchain.
So everyone sees the hash.
Everyone sees the hash. Peers, who are members of the collection, can verify the transaction against the actual private data and the hash. Peers who aren't members can still validate the transaction block by ensuring the hash is present and consistent with the endorsement policy for that collection. It provides integrity proof without revealing the contents.
Trust but verify, applied to sensitive data. Very neat.
Exactly. And PDCs have other features, like block to live, which lets you set data to automatically purge after a certain number of blocks useful for compliance or temporary secrets. You can also have separate endorsement policies just for the private data collection itself.
Okay, we have all the pieces: peers, orderers, ledgers, channels, identity, policies, chain code, private data. How does it all come together in a typical transaction flow?
It's generally described in 3 phases. Phase 1, endorsement. A client application crafts a transaction proposal. Basically, I want to run this function with these arguments and sends it to the specific peers required by the chain code's endorsement policy.
The client knows which peers to ask.
It needs to find out, yes, these endorsing peers then execute the requested chain code function. They simulate the transaction using their current view of the world state. But, and this is important, they don't update their ledger yet.
They just figure out what would happen.
Right. They generate the result, which includes the data that was read, the read set, and the data that would be written, the write set, and they digitally sign this result. This signed response is the endorsement.
And they send that back to the client app.
Correct. Phase 2, ordering. The client collects enough of these signed endorsements to satisfy the policy. It then bundles the original proposal and all the endorsements into a single transaction message and sends that to the ordering service.
Okay, transaction hits the orderers.
Yep. The orderers do their job. They receive transactions from potentially many clients, agree on a strict order, and package them into blocks.
In phase 3.
Phase 3, validation and commit. The orderers broadcast the newly formed blocks to all the peers on the channel. Now, every peer receives the block.
And they check everything inside.
They validate each transaction independently. First, they check the endorsements. Does this transaction have the required signatures from the right organizations according to the policy?
Makes sense.
What else? Second, and this is critical, they perform a read-write set validation. They look at the read set from the endorsement, the data the chain code read during simulation, and compare it to the current state of their own world state.
Why? What does that catch?
It catches conflicts. Between the time a transaction was endorsed and the time it gets committed in a block, other transactions might have changed the same data. This check ensures that the state the transaction was based on hasn't changed in a conflicting way. It prevents double spends and ensures consistency, especially for range queries which can suffer from phantom reads.
So if I tried to sell the same asset twice, the second transaction's read set check would likely fail because the asset's owner changed after the first one committed.
Exactly. If the read set check fails or if the endorsements aren't valid, the peer marks the transaction as invalid within the block.
And if both checks pass?
Then it's marked valid. Either way, valid or invalid, the peer appends the whole block to its blockchain log, the immutable history. But only the valid transactions cause updates to the peer's world state database. Invalid ones are recorded forever, but don't change the current state.
That whole flow, endorse, order, validate, it feels very deliberate. separating concerns.
It is. It's designed for concurrency, finality, and allowing different parts to scale. Very different from, say, Bitcoin's model.
Okay, this architectural stuff is fascinating. Let's shift slightly to the practical side. Operational considerations. What do you need to worry about when actually running Fabric?
Well, one big decision right at the start mentioned in the sources is the state database, CouchDB or LevelDB.
We touched on that. CouchDB for rich queries, LevelDB for speed.
Basically, yeah. CouchDB lets you do complex JSON queries if your data looks like that. LevelDB is simpler, key value.
Yeah.
But the key is you choose per peer when you set it up, and you cannot change it later without rebuilding everything. So you need to think hard about your application's needs up front.
Good warning. What else operationally?
Certificate management. We mentioned Fabric CA. Production networks need a solid process for issuing, renewing, and revoking certificates for all nodes and users. This is a huge security surface.
Right. And just keeping the lights on, monitoring.
Absolutely essential. Peers and orderers constantly grow their ledgers. You have to monitor disk space, CPU, memory. If a peer runs out of disk, it can't process new blocks. If an orderer cluster has issues, the whole channel can halt. So robust monitoring and resource planning are non-negotiable.
What about adding a new peer to a channel that's been running for a while? Fetching the whole history could take ages.
It could. That's where snapshots come in, according to the docs. A snapshot is like a compressed checkpoint of the ledger state at a certain block number.
So a new peer grabs the snapshot.
And then just fetches the block since the snapshot. Much faster onboarding.
Are there downsides to using snapshots?
Yeah, a couple of important ones. A peer that joined via snapshot cannot query the transaction history before that snapshot point. So if you need full historical auditability, you still need some peers with the complete history. Also, private data isn't in the snapshot. That needs to be reconciled separately, peer-to-peer, within the collection.
Okay, good caveats. And finally, configuration. Lots of settings files.
Oh yeah. Files like core.yamls for peers, and orderer.yaml for orderers control everything from network addresses and TLS security settings to database choices and logging verbosity. Getting these right is critical for stable and secure deployment.
Wow, okay, that was quite the journey through Hyperledger Fabric. We went from the basic idea of a shared, replicated ledger
To the specific roles of peers and orderers, the importance of that deterministic ordering.
explored how channels and private data collections handle privacy, which is so key for business.
Looked at Chaincode, the lifecycle, how business logic gets agreed upon and executed.
Dug into identity with MSPs, CAs, and the different kinds of policies that enforce the rules.
And finally, walked through that unique three-phase transaction flow and touched on the operational realities.
It really paints a picture of a complex but carefully architected system designed for specific enterprise needs managing trust, privacy, and governance among known parties.
Exactly. That shift from the potentially anonymous world of public chains to this trust but verify model within a defined consortium is fundamental to Fabric. The deterministic consensus, the policy engine, it enables different kinds of collaboration.
Which brings us to a final thought for you, drawing from all this. We've seen how Fabric prioritizes identity, controlled access, and partitioned privacy. How does building on this kind of platform change the game compared to designing for a wide-open public ledger?
Yeah, think about it. What new business processes or multi-party collaborations become practical or even possible when you have this level of granular control over who sees what and who can do what? But also, what new challenges arise in managing those identities and policies across organizations?
Definitely something to think about, the possibilities and the complexities. Thanks for digging deep with us today.
My pleasure. Great discussion.